Hey, welcome back. Nice to see you again. Hope you're all well. Today I got something a little different on my bench for repair. This is brought to me by a customer. This is not audio equipment at all. This is something totally different. This is a blower for a boiler. And what happened was this part broke on the customer. So what he had to do is run out and buy another one, which cost well over $400 for the replacement part. And this is the old one that didn't work. And he brought it to me, and he wants to see if I can look at it. And maybe it's an electronic problem that can be fixed. And then if it can be, fix it. And then he'll have a spare for standby. But anyways, this is the part numbers for the blower motor. I think this is the part numbers for the one that he purchased to replace this one. But I had to cover up his personal data here, so. But yeah, it's I can understand why he would want to have it looked at, because it's not a mechanical problem. So here's the motor itself and the blower. Get rid of this. As you see, the motor is not seized. It's flowing free. And if you take this cover off, there's just three little clips. There's a little bit of electronics here. And this is what I'm going to test out to make sure everything's working. There's a power input here, 120 volts, and then there's some signal and control wiring going to the central controller. Now, this fellow was kind enough to give me a note. What he figures was wrong. He wrote it all out. We'll go over that in a minute. He purchased, or not purchased, but on the interwebs, he found a data sheet, which is awesome, for the blower motor. And it's got a lot of information in here, and it's also got this, which is very valuable. It tells us how to interface it, and what kind of signals it's looking to expect to see. Pulse width modulation, 1 to 6 kilohertz, ground wire, plus 18 to 43 volts. That must be a supply for the logic. And yeah, this is awesome. So we look through this, we can help. And here's a line diagram for the boiler itself. I'm assuming it's a gas-fired boiler. Oh, yeah, here, gas valve. So yeah, it's a gas-powered boiler. It has a central microcontroller. It's got the blower down here. You can see the wiring for it. There's two sets of wires. One is green, W for white, and BK for black, and that must be the 120 volts, and that comes from this block here, which is the power feed. Yeah, this is a power feed here. So it feeds power into the blower, and then it has looks like 3 wires, green, black, and red, which goes to the microcontroller. So those are your signals. And from what I can tell, the controller itself has a lot of features built into it. I think I was reading some of it here. Motor electronics integrated in the blower unit with startup current limit, reverse battery protection using plug coating, locked rotor protection, and overload protection is optional. So yeah, it's a good design. I think this is made in Germany. Yeah, this one's made in Germany, and well engineered, well thought out. It's got lots of protection built on it. So let's see what we can do to get this thing going again. We have data sheets here. We could probably even hook it up to power, and maybe you can have it spin up for us and find out what's wrong. So let's look at what he wrote. He wrote a little note here. It says, when blower is supposed to be stopped, there should be about 32 volts DC measured between black and red wires on the comm harness. So that's the communication harness, I believe. And yeah, it's said here works between 18 and 48 volts. So 32 volts is within that range. Actual measured was 39 volts DC. When the boiler was powered up with a new blower, the blower turned for about 1 revolution, then stopped. So it's probably doing some power on initialization or something. With the old blower installed, it continued to spin at idle speed when the blower was powered up. So it's probably not responding to the control signals. This is the Comm connector here. It's a 5-pin. I can see an Opto Isolator right beside it. And I don't know what these chips are. I can't read. They're all... it's kind of conformal coded too. 120 volts in this side. We have some standard across the line cap, common mode choke, across the line cap, fuse. There is a fuse here. It is a 2 amp, 250 volt fuse. That's a little round thing. Diode bridge. And then there's a chopper transistor, which is an IRF 830. That's a MOSFET then. Looks like a MOSFET. Main filter cap for the power supply, this power supply, and then chopper. And then we have 4 driver transistors for the motor. So this part here is probably opto isolated. It is opto isolated. I can see it on both. Yes. So this whole thing here is opto isolated, and this part here is all lines live. So it shouldn't be too hard to figure out. The main problem would be getting the circuit board out, because there are screws from underneath holding it to the motor and connections there. And it looks like I would have to take this apart. Anyways, let's have a look at it. Okay, before I go too much farther, what I think I want to do is I want to put 120 volts on this connector, and I want to see if it behaves the way he wrote up in his little write-up there. I want to see if it does that slow spin like he said. But first, there's 3 pins here. I want to make sure I don't connect my my cheater cord, or Widowmaker I like to call it, to the wrong pins, because since there's 3, there's probably a ground here too. So I just want to get my continuity tester and figure out which is ground. It's probably the center. Nope. There, it's that one's the ground. So let's connect our Widowmaker to the other 2, and we'll feed it 120 volts. I'll feed it through an isolation transformer so that we can't. Okay. Okay, here we go. Turning it on. Okay. So it should be powered up, do 1 revolution, and then go into sleep mode, and that's not what it's doing. So let's, I got the power off. Let's take a look at this. Like, I don't obviously see anything burnt, and we are getting power. I'm assuming that fuse is good because we got power through it. And there are some what looks like fusible resistors here. This one is it's hard to say, I don't know. And a few capacitors. Okay, let's have a look here. That's awfully loose. Oh, well, you look at that. Looky, looky here. I don't know if you can see down below that cap, but that one lead from the capacitor is completely sheared off and gone. Will you look at that? Let me pull this out. Can you see it? This cap is not in circuit for sure. And it's a 150 microfarad, 250 volt. Okay, so we're gonna have to replace that cap. How to get the board out? So, I think we might have to pull off the blower to get this all apart. Because I think it's one shaft. Yes, it is. Okay. Like I can remove this screw here, but that does nothing for me whatsoever. I have to get onto the other side of that board so I can solder a new capacitor in. And yeah, okay, so let's take this off, I guess. Wrong size. All right. Okay. Now we're going to have to remove this fan. What I'd like to do is remove this spring clamp here, and then let's see if I can do that. I need a good screwdriver. Don't want to break that, that's the main thing. I don't want to break anything here. I might have to fight with this off the camera. It's going to have to come off because I need to remove these three to get the blower housing off, and then I can access the screws that are underneath for the motor, and then separate from this the printed circuit board from this plate. See, I got one screw in there hidden, right in there, and then there's another one on this side. Is there two or three? There's probably three. No, there's only two. So I got to get those two out. So let me pause camera here. I'll see if I can get this turbine off, and then we'll continue. All right, I think I got this figured out. Two screwdrivers. Very, very carefully pry up on this. This is plastic, so don't force it. You don't want to crack anything. Just very slowly. It slides very easily. Up she comes. There we go. And that's our clamp. So we should be able to get this off. It's very rusty though, so I don't know. I'm gonna need more prying tools here, I think. Okay, so what I determined is this rust on the end of the shaft here is what's holding this turbine on. So I'm just gonna take a scour pad and remove whatever rust I can. What I did is I pushed it all the way on. And I'm trying to get it a little bit smoother because it's really, the rust is really gripping the plastic and it does not want to go past. I might have to get some sandpaper. This stuff, Scotch Brite, is not cutting it. Alright, so I did manage to get it. What I used is a screwdriver and tapped on it. I used light taps, didn't want to hit it hard. And I didn't crack anything, which is what I wanted. You can see the shaft is quite rusty. But now we got take this plate off and we can get in and do our repair. only got one screw holding here. It's a ground screw. And we have a standoff here. Okay. Now we got access. And you can see that this looks like it was overheating. Maybe that was arcing there. Let's get a little closer. All right, so we're in. And this little insulator, I gotta remember to put that back. Another thing to mention, this motor has ball bearings, so it's not something you can re-lubricate. If these bearings go noisy or start seizing up, you can probably remove the screws on this motor, take this motor apart and replace those bearings, which shouldn't be a problem. Looks like they're just probably a standard size, but they feel really good. Like, there's no play in them. No noise. Okay. Anyways, this connection here is the exact opposite of where we lost our lead on the capacitor. It looks like it was overheating here. Don't think that's anything else, but let's see if we can get this capacitor out. Might have to add some fresh solder here. Time to clean the bench. I hate working on equipment with conformal coatings. It's a pain in the butt. Okay, so we got that nice and hot now. Legless capacitor. I wonder if there's a charge on there. Check before I start fooling around. Okay, let's hook it up to a cap meter. It looks like it's broken. Maybe from vibration it broke. Okay, let's see, negative. It's not leaking, and I don't see any corrosion here, and the capacitor tests good. It's at 161 microfarads, and our ESR is 250 milliohms. This is a good capacitor. It's just that I got a broken lead on it. So let's get another capacitor, 250 volts, 150 microfarad. I'll see what I got in stock here. I should have something that'll fit the board and do the business. I'll clean up those holes and then we'll install it. Alright, so this is what I settled on. It is a 220 microfarad at 250 volts, and it has to be the same height because we have a clearance restriction. If we put the cover on, there's clearance issues with anything taller than what's already there. So this is, and we got lots of extra real estate. It's wide enough to fit the board. It's got lots of room. And most importantly, it has the solder lugs instead of the wires. So this will be secured down quite a bit better. And then I'll also secure it with some adhesive down to the board as well. And there won't be any more vibration issues. Okay, so negative. This is our negative ground plane here. And yes, I did check. Get this pushed in. Might have to adjust these. It's nice and tight. Let me see if I can. There we go. Oh yeah. And you want it pushed down flat to the board as much as possible, because you don't want any vibration or movement between the part and the board. That's why leads break. Okay. And hold the soldering iron there, let that heat up, because if we want it to flow right through, that's a plated through hole. We want that joint good and hot. Okay. And then I'll do it again once I'm pushing on it, just to make sure it's seated. Okay. Here we go. And it's not going to move. And like I said, I'll put silicone to anchor it. So let's clean off that board. Some alcohol. Sorry. It must have been running for a while to get hot like that. You see how it got the board hot? Cooked it. Now we need some silicone. Okay, so I got silicone here. I'm going to put a blob here. Put one over on the other side. Beside that resistor. Put too much, and I'll put one over here. And then once that sets up, that capacitor is not going anywhere. And the thing about silicone is you can easily cut it with a knife. And if you want to get that part out, that's no problem. Okay, I'll reassemble this. I'm not doing anything with the bearings, they're fine. I'll ESR these other two caps though, just to make sure. I don't think there's anything wrong with them. Stupid coatings. Yeah, that one's good. And this one. 2.1 ohms, and that is 10 microfarad at 50 volt. That's good. All right, I'm going to put this together and we're done. All right, so one thing I want to do before I assemble is I want to give this a test, because once I assemble it, I'll have no access to the bottom side of the board, and we'll see how this goes. Let's put some power to it. I'll put power to the AC input, and we'll see what it does. Okay, switching it on. Okay, it looks like it was running full speed, open loop, but then it looked like it kind of regulated itself. I don't know if you heard that. Let's try it again. No. So it's running full speed, but let's see here. This here on the data sheet says pulse width modulation. You got, let me back up a bit here. Before I get too much farther, I want to explain what I see here. So I gave this circuit a looking over, and this is the AC input. There's across the line caps, there's a common mode choke, there's a fuse, bridge rectifier. So this is a basic, you know, and then we have our main filter cap. This MOSFET here that I can tell, as far as I can tell, this little circuit here provides 12 volts for the rest of this circuit here. And you can see it kind of on this side and on this side, and then there's two wires that run across and feed all this. Now the main power comes in through here, goes through this filtering, this rectification, this filtering, and it goes this way to this bank of 4 transistors. And I think this is an H bridge, to tell you the truth. I think what they're doing here is there's only 2 connections to the motor windings, and I think with the H bridge what they're doing is they're synthesizing an AC signal to run this fan motor at whatever speed they choose. And this supporting circuitry here handles all of that. There's these 2 are run in pairs, and these 2 are run in pairs, and there's a pair of small SOT 8s, or SOT 8-pin SOT ICs, and I think these circuits here create the signal to run the motor, and this drives it. What am I getting at? Well, here, this circuit here is completely isolated from the rest of it, and it's run through 2 opto isolators. This opto isolator here, if I go back here and look at the motor, there is a Hall effect sensor that senses the speed of the motor, how many rotations per minute, and it feeds it back to here, and from here it goes up and runs over to this opto isolator, which sends the feedback to the microcontroller of the boiler. Now this opto isolator is feeding a circuit, or feeding a signal through this way. So there's a diode here, a light emitting diode, and then there's a photodiode and transistor on this side that are picking up the light signal and telling this circuit to turn on or off or what. And there's a pulse width modulation they're talking about here. This is the signal I'm talking about through this opto isolator. It starts up the motor at least greater than 20% PWM. It's a digital PWM. When PWM is low, the blower is off. When the PWM is high, the blower is on. So I think this might not be getting a signal to turn the blower off. So what I'm going to do is I'm going to feed it a current on this side, the LED, and what I'll do is I'll tack on another LED so that we can see the status of it, and I'll put a series limiting resistor in there, and then we'll power up that LED, and we'll see if this LED controls this motor. If it does, then we're golden and we're going to get it working. Alright, so what I've done is I connected to the internal LED on the opto isolator is I connected a external LED in series with it so that we can see when it's turned on and off, and then I got a 1K series dropping resistor here, and I think I'm ready to do a test. If I do a test on this little circuit, if I connect the negative, I don't know if you can see that, but the LED lights up. I don't think I got maybe 10 milliamps flowing through there, not very much. Enough to turn the LED on. So I'm going to power this up, and we're going to test to see if the controller on this board has any reaction to the input. Okay, look at that. It shut the motor down as soon as I connected. So this is working. I can control the motor by turning off the LED inside that opto isolator. So we can probably demonstrate pulse width modulation too. We could feed it a pulse width signal and we can control the speed of this fan. So let's do that next. Alright, so what I've done is I hooked up, instead of a power supply feeding 10 volts, I got it hooked up to my signal generator, and it's going to feed a duty cycle. I don't even know what frequency it is. Let me see here. It says it's, oh, it's 1 kilohertz and 6.9 volts. And then I have a 5 volt offset. So this LED will light up. Here, I'll show you. Turn up the... you can see the light come on. I don't know if you can see it in the camera. It's pretty bad LED. But I'll set it to 0 right now, and it should run at full speed when I turn this fan on. And then I'll turn up the duty cycle. And 50%, 60, 70, 80, 90, 90%. But you can see the fan is controllable by speed, by the pulse width modulation signal. So everything's good here. I'm going to shut this off. I'm going to put everything back together, and I'm going to give it back to the customer and say it's working. And he can use this as a spare part now. And if his blower motor goes again, and he's got a spare on hand. All right, let's try this one more time. Seems I'm having camera problems. Out of the blue, it just gives me an error message, cannot record. So maybe it's time for a new camera. But anyways, I just want to wrap this up. It's all back together, and seems to be working. So I'm going to send this back to the customer. It's a shame that he had to spend $400 to replace a part that was just a failed capacitor lead. Even the capacitor is not, the capacitor didn't fail, the lead failed, and I guess that's from vibration, because that's the only way one of these wires is going to break. You know, it's not from excessive current, or it wasn't corrosion, because there's no leakage here. It just snapped off, and I think it was poor mounting and vibration that did it. So we got a new capacitor in there now, and it seems to be working. So I'll return this, and yeah, I just want to say thanks for the service info. That was really helpful, doing a lot of the internet searches for me already, and saved me a lot of time. So yeah, it's success. All right, result. Take care, and thanks for watching.